For decades, we've been stuck in a tough spot with organ transplants. The demand completely crushes the supply. But what if we could change the game entirely? What if instead of waiting for a donor, we could just print a new organ when we need one? Today, we're jumping into the absolutely revolutionary science of 3D bioprinting. To really get why this is such a big deal, let's start with a number: over 100,000. Right now, that's how many people are on the National Organ Transplant waitlist, and that's just in the United States. And then there's the much, much harsher number, 20. That's how many of those people die every single day, just waiting. The system as it is, well, it's just not working. But what if there was a totally different way? This is the question that's fueling an entire field of research. Can we actually solve this crisis by literally manufacturing human organs made to order? You see, the ultimate goal here isn't just to make more organs, it's about making better organs. The real promise is total personalization, creating an organ that is custom built for you so your body accepts it without a fight. No more risk of rejection. This personalization breaks down into two key ideas. First, you have anatomical personalization. This means using your own MRI or CT scan to print an organ that physically fits your body perfectly. Then you have biological personalization. This means using your very own cells, so your immune system looks at the new organ and says, "Yep, that belongs here." So how in the world do you actually print living tissue? It's more complicated than just hitting print. The process happens in three main stages. First is pre-printing, which is about creating the digital blueprint. Then comes the actual printing. And finally, you have post-printing. This is where the printed structure actually matures into living, working tissue. The secret sauce to all of this is a substance called bioink. This isn't like the ink in your pen. It's a complex, living cocktail of gels for structure, special molecules that tell cells what to do, and most importantly, the patient's own living cells. It's a printable recipe for life. After printing, the structure goes into a bioreactor. You can think of it like a high-tech oven for living tissue. It pumps in nutrients, gets rid of waste, and even applies tiny forces to train the cells, teaching them how to work together as a real organ. But where do all these cells come from? This is where a Nobel Prize-winning technology comes in. Scientists can take a simple skin or blood cell from you, rewind its clock to turn it back into a super powerful stem cell, and then they can tell that cell to become any type of cell they need: heart, liver, kidney, you name it. Now, I know what you're probably thinking. If we can do all this, why can't I order a new kidney online yet? Well, the entire field has been banging its head against one massive wall for decades. It's often called the Great Wall of Bioprinting, and its name is the vascularization problem. Think of it like this. You can't just build a city with a bunch of skyscrapers. A city needs roads, power lines, and plumbing to function. An organ is the same. It needs a network of blood vessels. Without it, any tissue thicker than a sheet of paper will just starve and die. Trying to print that tiny, complex plumbing system is the most important challenge in tissue engineering. So how are scientists getting past this great wall? They're engineering clever ways to go right through it. They're using things like sacrificial bioinks that they can print and then just melt away, leaving behind hollow tunnels that become blood vessels. They've also invented techniques like fresh printing to keep soft tissues from turning into a puddle. To get your head around fresh printing, just picture Jell-O. Imagine trying to 3D print a detailed sculpture using soft, jiggly Jell-O. It would just collapse into a blob, right? Fresh printing solves this by printing inside a supportive bath of gel, which holds everything in its proper shape. So has any of this technology made it into a human patient? The answer is yes, but we are on the first few rungs of a very tall ladder. A huge moment was way back in 2006 with the Atala bladder, which proved lab-grown organs could work in people. The first truly 3D bioprinted living implant just happened in 2022, an ear called Ori Novo. An ear was chosen because cartilage has no blood vessels, which was a genius way to sidestep the vascularization problem. This brings us back to the ultimate promise. A conventional transplant isn't really a cure, it's a trade. You trade your failing organ for a lifetime of powerful toxic immunosuppressant drugs, but a bioprinted organ from your own cells doesn't need any of that. It's not a trade, it's a true cure.
But even if the science is perfected, enormous hurdles remain. Who's going to be able to afford this? If a printed organ fails, who's legally responsible? And how do you even regulate something like this? Is it a medical device, a drug, or something entirely different? We have to be realistic about the timeline. Over the next 10 years, you can probably expect to see things like cartilage and skin become a reality. But the holy grail, complex organs like kidneys and hearts, is likely still 20 years away, maybe more. While we're waiting, the technology is being used right now to print tiny organs on a chip. These aren't for transplants, but they let drug companies test new medicines on tiny bits of human tissue. This makes research faster, cheaper, and helps us move away from animal testing. Look, bioprinting has the potential to fundamentally change medicine forever. It could offer a cure for one of our most difficult problems. But the question is this really the future? Or will the huge scientific, ethical, and financial hurdles just prove to be too high to overcome?